Hello everyone and welcome to the presentation of MAGIC, a magnetic resonance coupling intra-body communication system. My name is Stella Banou. I'm one of the authors and a PhD candidate at Northeastern University in Boston, Massachusetts. I research intra-body communication methods and explore how they can innovate the world of IoT. We're now one step closer than ever at connecting the human body with smart intra-body networks thanks to the advancements of sensor technology, computational power, and communication systems. We're able to place small biocompatible devices in all our major organs to have constant critical monitoring and offer life-changing treatments. Intra-body sensor networks allow us to monitor important health metrics and gather biological data critical to treatment. More than that, communication between sensors in the body is vital to taking it a step further and allowing for a lot more innovative applications, such as controlled drug delivery within the body, as well as raising alerts when abnormal measurements are sensed. Some considerations that are important to keep in mind when designing wireless body sensor networks are size, power limits, and reliability. Size is important for obvious reasons. Miniaturization of implantable devices is essential in order to have efficient and safe systems. Power limits are important both because we have battery-powered sensors, but also the thermal power of those sensors needs to be limited for the safety of human tissue. And finally, reliability in terms of links between sensors, but also the ability of the system to quickly transmit health-critical information. Timely communication of critical information is the area in which this paper makes a significant contribution. We have established until now the need for remote health monitoring and symptom monitoring for early detection, more now than ever with the worldwide health crisis that we are in. Researchers for years have been able to work in micro and nanoscale sensors, from deep brain sensing to ingestible cameras for gut health monitoring. Our task with MAGIC is to ensure that the timely communication between sensors is achieved to have optimal use of body sensor networks. Our first task in designing MAGIC was to identify the most suitable intra-body method by comparing the state of the art. RF communication has been used for intra-body networks in the past and has some limitations related to its high attenuation through tissue. More power is needed to get the signal to travel through the body using RF, which makes it power inefficient. Additionally, the range safety trade-off is creating problems, since in order to overcome attenuation, the solution of raising output power is always limited by safety standards. Alternative coupling methods have been used for intra-body communication, such as capacitive and galvanic coupling. Capacitive coupling works by transmitting information through coupled electrodes to human tissue with a return path via common ground. Galvanic coupling uses the coupling between two transmitting and two receiving electrodes to transmit information. Both have limitations, which make them unsuitable for an implantable network, such as the one that we're envisioning. In the capacitive coupling case, the common ground requirement makes it unsuitable for an implanted network. In the galvanic coupling case, it is sensitive to node location and tissue composition. We concluded that the method most suitable for the real-time intra-body network that we envision is magnetic resonance coupling. Magnetic resonance coupling intra-body communication works by placing resonating coils in or on the body in the form of wearables or implants, and modulating the magnetic field between them to send information. MAGIC is a network of nodes communicating by magnetic resonance coupling. Our communication system modulates magnetic waves to transmit information along a line network of coils, such as the one you can see on the screen. Each coil is attached to a node of our network. Manipulation of the resonance balance between the coils of our network can raise real-time critical alerts along the network, and we have designed our system to perform that kind of alert notification. Our three main contributions are a theoretical framework for relay coils in the miniaturized near-field magnetic communication, software and hardware system design for real-time alert transmissions throughout the body, and a testbed implementation for system evaluation and comparison with competing technologies. Starting from the energy relay coils, in order to explain the theory behind relaying coils, we take an example of 5 nodes, such as the one that you can see on the screen, represented by 5 circuits. Each circuit is in resonance. What that means is that the inductance L and capacitance C of each circuit fulfill the resonance equations that you can see in the bottom of the screen. Node 1 is the transmitting coil, which transmits a signal by modulating the magnetic field. The magnetic field propagates from node to node until it is sensed by the receiving node, which is node 5. The passive intermediate nodes, 2 to 4, enhance the magnetic flux density, which is a way of measuring the magnetic field. In order to achieve optimal signal transfer between transmitter and receiver through the passive nodes, the mutual inductances M are all equal. The current at node 5, which is a receiver, depends on the resonance, the voltage and current that is applied on node A or node 1, and the resonating currents of the intermediate nodes. In order to better understand the resonating energy relay coils, we created a simulation on console. On the top of the screen, we can see the scenario for simulation in which two equally sized coils are placed in a muscle tissue environment, resonating at a selected frequency. We measure magnetic flux density at the cross-section of the two coils. We see a high density around the source coil due to the applied voltage, and a much smaller density at the destination coil due to signal attenuation. When we focus on the bottom of the screen, in this instance of our simulation, we have added an intermediate passive resonating coil of the same size. We notice that the magnetic flux density at the destination coil increases, and that is due to the effect of the relay coil. To summarize, the presence of the resonating relay coil increases the magnetic flux density, which in turn increases the current displacement at the destination coil. We created a second simulation with 5 resonating coils this time and studied the parameters that affected the received voltage at the destination coil. In the first study, we investigate the effect of coil size and resonant frequency. As we can see in the screen, the received voltage, y-axis, is highest for all coil sizes at the frequency of 3.39 megahertz. That is the frequency at which we designed our simulated circuits to resonate. This finding proves that once a circuit is designed to resonate at a specific frequency by selecting the L and C, the highest received voltage will always occur at that frequency. In terms of coil size, the largest coils offers the highest received voltage, since it has a higher magnetic flux density and higher coupling. We also investigate the effect of the medium in which the coils are placed to its magnetic flux density. We notice very small differences, both in magnetic flux density at source and destination, and also the current at the destination coil between air, muscle, and skin. What this proves is that the system, based on magnetic resonance, can have similar behavior whether it's in the air as a wearable, on the skin as a wearable or implant, or inside the muscle as an implant. We move on to describe Magic's system design. We will first see the communication system design of a single link. It consists of a transmitter circuit, which is a simple magnetic resonance circuit. The coil inductance and capacitance is designed to operate at 3.39 megahertz in resonance. The size of the coils that can be implanted in the body safely, as well as the frequencies that are typically used in magnetic resonance systems in or near the body, were the guides that we used to decide the inductance and capacitance values from the table. On the receiver side, the resonating circuit feeds into the rest of our circuit design in order to produce a square pulse to be demodulated by the receiver MCU. We selected the OOK modulation scheme for simplicity. We continued to expand the single link design into an alert network. As we can recall from the energy relay theory, we have created a network of nodes, each of which is attached to a coil antenna. For the purpose of our implementation, we used 2 centimeter diameter antennas. The relays B, C, and D are all passive, which means that they don't have any power applied to them. The transmitting node modulates the magnetic field by applying a voltage signal to the coil. Each node has 2 capacitance options connected to their coil, a resonating capacitance, C-res, and an alert capacitance, C-alert. C-alert is unique to each coil. When all the nodes have the resonating capacitances connected, as we can see on the screen, typical magnetic resonance communication takes place to send sense data across the network. When relay C switches from the C resonance to the C alert, we immediately see a distress in the magnetic field, which is called by breaking resonance, and in turn, that affects the voltage across the coil of the receiving node, Rx. To further study that effect, we plotted the received voltage at node 5 versus the capacitance of the intermediate relay nodes. We see that when each node switches to its dedicated capacitance, 1, 2, or 3, the voltage at the receiver is between specific thresholds. From this, we can deduce that the destination coil not only can sense changes in the received voltage, but it can also know which capacitance value was applied, and therefore know which coil was the one that raised the alert. We did design the protocol logic for node addressing, channel access, and generating alerts. And I will not go over the flowcharts right now in interest of time, but those are very thoroughly explained in the paper for anyone that's interested. Moving on to the system implementation and evaluation, we started by building a 5-node network spanning 50 centimeters over the air. The transmitter of our system on the screen modulates the current, the voltage that is applied to the coil to send a signal. And then the receiver is running our receiver logic. Following that, we also built a single hop system in the muscle of our human tissue phantom and measured the bit error rate. Finally, we imitated a wearable implant communication scenario in which the transmitter is in the muscle. It cannot be seen in the screen, but it is underneath that phantom. And the receiver is a few centimeters above the air. All configurations have similar bit error rate due to the fact that our distances were kept constant. And as mentioned previously, the medium of communication does not affect the magnetic resonance as long as it is similar to air in terms of permeability, as is human tissue. We moved on to measure the bit error rate of MAGIC in different versions by varying the number of equidistant nodes that are placed as relay nodes between transmitter and receiver. We also vary the transmit power. We identify 1.2 dBm as a transmit power, which provides a low bit error rate, but only once at least 2 intermediate relays are introduced. We simulated our 5-node system in order to ensure its safety, and we measured what the magnetic field strength is throughout the 5-node system when a 1.2 dBm TX power is applied. And we measured that the electromagnetic field strength is 3.81 times 10 to the minus 6 milliwatts per centimeter square. The measurement is important because it is below the maximum permeable exposure limits set by IC and IPR, which is 2.02 milliwatts per centimeter square. Moving on, we compared the power consumption of MAGIC with similar intrabody networks using radio frequency in the ultra-wideband and galvanic coupling. The outcome of this comparison is that MAGIC has a lower power consumption than both methods, which is mainly due to its passive relays. Due to the fact that any additional node is a passive node, by expanding a 3-node network to a 5-node network, we do not see an increase in power consumption as we see in other competing methods. We also measured the delay of MAGIC in both the 3-node and the 5-node version. A similar trend to that of power consumption appears when compared with TDMA and galvanic coupling. For the TDMA case, we used the worst case scenario that we found in literature. MAGIC has slightly higher delays than TDMA, lower than galvanic coupling, and still maintains stable delay independent of its network size. The single hop delays were also measured in the experimental setups that I showed you before in the pictures. As we mentioned previously, the medium at which the system was built, whether it's air, muscle, or skin, does not have a big effect on its delays. The reason we keep mentioning delay and timing of our system is because we claimed in the beginning of our presentation that Magic offers near-instant timely alerts. In order to test that, we placed an oscilloscope on a probe of the oscilloscope on the receiving coil of our network, of our implemented network, and another probe on the intermediate node that was supposed to send an alert by switching to its C alert. As we see on the oscilloscope screenshot, when the voltage across C alert in one of the intermediate nodes rises, meaning that C alert is connected to the coil, the destination coil voltage drops instantly, indicating that a disturbance of resonance across the network can be sensed in real time, making Magic a very suitable real-time instant alert system. To conclude, we have presented a testbed implementation of Magic, which is an implant network with a real-time alert system. We ensured the safety of our system by comparing its electromagnetic field to the maximum permissible exposure limits. We created a 50 centimeter range scalable network that can include implants and wearables. In the future, we would like to create a full protocol stack for our network with medium access and error detection. Also identify suitable modulation scheme to achieve lower bit error rate and higher data rates. And finally, investigate the effects of miniaturizing to the millimeter scale coils, which are more realistic to the functionality of our network. Thank you very much for watching the presentation. I am open to any questions during the conference.